What if everything you think you know about the universe is wrong? From the second we wake up, we trust our senses. The ground feels solid, the sun feels warm, the world feels real. But physics tells us something very different. Zoom in far enough, and that solid floor, it's almost entirely empty space. The atoms in your body, over 99.999% nothing. And the particles inside those atoms, they don't even take on definite properties, unless someone's watching. That sounds impossible, but it's been tested, measured, and confirmed again and again. In fact, the closer scientists look, the more the illusion starts to fall apart. At some point, the question stopped being, how does the universe work? And became, is the universe even real? That's not an exaggeration. It's the shift physics is undergoing right now. We used to think the universe was made of things, atoms, matter, space, and time, all ticking away, whether we were watching or not. But experiment after experiment keeps showing the same thing. What we call reality may not be built out of stuff, but out of information. This isn't science fiction. This isn't a metaphor. This is quantum mechanics, one of the most successful, accurate scientific theories we've ever had. And yet, it's telling us something we're still struggling to accept. Reality might not be something out there. It might be something that emerges only when we look. Let's step back. For centuries, science was built on two big ideas. One, that things exist independently of us, and two, that those things are separate from each other. But quantum physics breaks both. We've seen particles affect each other across space with no connection. Not a theory, an experiment. Two entangled particles, moved far apart, still act like one. Change one here, the other changes there. Instantly. It doesn't matter how far. It doesn't matter if they're light years apart. There's no delay, no signal, no force traveling between them. It's as if space itself doesn't exist, as if distance is an illusion. And that's not all. We've also found that particles don't decide on their properties, like position or momentum, until they're measured. Before that, they're just possibilities, a range of outcomes waiting to collapse. In other words, the universe isn't waiting in a fixed state for us to discover it. It's waiting to be defined by interaction. And if you're thinking, okay, but that's just the quantum world, that's tiny stuff, think again. The effects ripple out into everything, including you. Because here's the part most people miss. Your brain has never actually seen anything. It doesn't receive objects, it receives signals. Your eyes translate light into electricity. Your ears turn pressure into voltage. Your skin converts temperature into current. Your brain isn't watching the world. It's interpreting it, constructing a model, piecing together meaning from patterns. So what you experience isn't the world. It's your version of it, a simulation, built in real time. Now, if the universe only renders when observed, and if the mind only experiences the rendered result, then what's underneath all of it? Some physicists now believe nothing we'd recognize. No objects, no space, no particles, just data, information, encoded patterns, like the ones in a video game, only much, much more complex. And when a measurement happens, when something is observed, that data becomes real. So what we're living in may not be a collection of physical things at all. It may be a process, a dynamic, responsive system, where reality is produced as needed, not before, not after. Just when the question is asked, it's no longer a stretch to say, reality, as you know it, might not exist. At least, not in the way we thought. So what does exist? That's what this video is about. Not wild guesses, not mind games. Just the tested, peer-reviewed evidence that physicists have gathered. Evidence that suggests the universe isn't made of stuff, but of relationships, of questions, of interactions. And if that's true, if we're not just living in the universe but generating it, then everything changes, from how we think about the cosmos to how we think about ourselves. The universe seems solid, but it isn't. Let's get clear first. The universe feels solid. It looks real. It's tangible, predictable. Right now, you can probably feel the ground beneath your feet or the chair you're sitting on. We're so accustomed to the world being real, so comfortable with the idea that everything we interact with is solid, that we rarely stop to question it. But here's the thing. It's all an illusion. What does that even mean? If you're touching something right now, like your keyboard or the cup in your hand, it sure feels like you're making contact. But at a deeper level, you're not. The atoms in your hand are coming into contact with the atoms of whatever you're touching, right? Well, that's true, but here's where it gets strange. Atoms are not what they seem. They're mostly empty space. The core of an atom, the nucleus, is incredibly tiny. The electrons, the particles that orbit the nucleus, are even smaller and spread out far from the center. When your hand makes contact with your phone or keyboard, the outer layers of your atoms are interacting with the outer layers of the atoms in whatever you're touching. But these outer layers don't actually touch anything. What you're really feeling is something called resistance. It's the electromagnetic force between the atoms in your hand and the atoms of the object you're interacting with. Electrons in the atoms of your hand repel electrons in the object's atoms, creating a force that we experience as touch. But this isn't real physical contact. It's more of a pushback. It's not touching. It's interacting. An invisible dance of forces, all governed by fields and energy. So what you're really feeling isn't solid objects, but the resistance created by these fields. Now let's zoom out a little, get further into the heart of things. You're probably thinking, okay, but atoms are still real, right? They're the building blocks of everything. It still feels like my hand is touching my phone. What's the big deal? But here's where things get even weirder. Atoms themselves, those things that make up everything we see and touch, are not as solid as they seem either. They are, in fact, more like, well, events. Instead of being little balls that are sitting there in one place like tiny marbles, atoms are more like ripples in fields. Particles, those building blocks of reality, don't just exist in one location. They pop in and out of existence, like brief flashes of energy showing up in the field only when we observe them. And sometimes they don't seem to exist at all unless we look for them. They exist as probabilities, floating in a strange in-between state of maybe. They're not objects, they are probabilities. So when we say we're touching something, are we really touching it? Or are we just interacting with a field of probabilities? Think about that for a moment. We live in a world where the things we think are real, the things we think are solid, might not be solid at all. The very fabric of reality, the particles that make up the universe, exist in a weird, uncertain state, neither fully here nor fully gone. That cup you're holding? It's made up of atoms, yes, but those atoms are made of energy, and that energy doesn't always behave like you'd expect. In fact, the more you zoom in on reality, the more bizarre it becomes. If you take a step back and look at this from a distance, from the perspective of science, it starts to become a cosmic riddle. If we never really touch anything, if everything we experience is just fields and energy bouncing around, then what exactly are we interacting with? What is this thing we call reality? Is it just an illusion we've agreed upon? Or is there something deeper going on, something beyond our ability to fully grasp with our senses? This problem doesn't stop here. It stretches out across everything in our universe, from the tiniest particles that don't seem to fully exist to the vastness of the cosmos itself. The whole thing is built on this strange, elusive foundation. It's as if reality is this giant cosmic puzzle, and the pieces don't quite fit. The rules we use to navigate our world, what we call solid and real, might just be an approximation, a model our brains have built to make sense of a universe far stranger than we could ever imagine. The more we look at it, the more it seems like everything is connected, or more accurately, entangled in ways we don't fully understand. So here's the question. If nothing is really solid, if everything we think we know about touch and reality is, at its core, an illusion, then how can we trust anything we see or feel? If reality is not as real as we think, what does that mean for the universe we live in? Are we just passengers in a strange dream? Or is this something else, something bigger than we can see, something that we are still just beginning to understand? We might not have answers to these questions yet, but one thing is certain: the universe isn't what it seems, and that in itself is a mystery worth exploring. Einstein versus quantum mechanics. In the mid-1930s, a bold challenge was thrown at the heart of a revolutionary new theory: quantum mechanics. The problem? Its strangeness. To grasp the tension between classical physics and quantum physics, we need to go back to one of the brightest minds in history, Albert Einstein. Einstein was no stranger to groundbreaking ideas. His theories of relativity had already shattered the old perceptions of space and time. But, as brilliant as he was, Einstein didn't always embrace every new theory that came along. In fact, he had deep reservations about the strange world of quantum mechanics. In 1935, Einstein, along with two of his colleagues, Boris Podolsky and Nathan Rosen, published a paper that would become a cornerstone of the ongoing debate between two very different views of reality. This paper, famously known as the EPR paradox, after the author's initials, wasn't just a critique of quantum mechanics. It was a challenge to the very foundation of the theory. The question they posed was deceptively simple: can quantum mechanics truly describe physical reality? To understand why Einstein and his colleagues asked this question, we need to look at how the universe had been perceived up until then. For centuries, physics had been dominated by the classical views of Isaac Newton and others. The universe, according to this traditional view, was a grand machine. Each part had its place, each effect had its cause, and everything followed clear, deterministic laws. The sun rose every morning, planets followed predictable orbits, and if you knew the positions and speeds of all the particles in the universe, you could, in theory, predict the future. But quantum mechanics, this strange new theory that had been developing in the 20th century, seemed to throw that view out the window. Quantum mechanics proposed that the world at the smallest scales was anything but predictable. It told us that particles could be in two places at once. It told us that the very act of observing something could change its behavior. It told us that two particles, separated by vast distances, could somehow be linked in a way that meant a change to one would affect the other instantly. Einstein, whose mind was used to order and precision, found all of this hard to swallow. In his eyes, quantum mechanics wasn't just bizarre, it was deeply flawed. He famously referred to this instantaneous, distant connection between particles as spooky action at a distance. To him, the idea that particles could affect each other without anything physically connecting them just didn't sit right. There had to be some hidden variables at work, something underlying the apparent randomness that quantum mechanics described. It was like a magician's trick. There had to be something going on behind the scenes that we just hadn't discovered yet. This stance made Einstein a kind of intellectual outsider when it came to quantum theory. While the rest of the scientific community was starting to embrace quantum mechanics, particularly with the work of people like Niels Bohr and Werner Heisenberg, Einstein was skeptical. His belief in a deterministic universe, one where everything had its cause, made it difficult for him to accept the inherent uncertainty at the heart of quantum physics. For Einstein, the universe wasn't a place of randomness. It was a place of laws, where things happened for a reason, where causes led to effects in a predictable manner. If quantum mechanics couldn't explain that, then it had to be incomplete. He once said, "God does not play dice with the universe," summing up his belief that there must be a deeper order to reality, one that quantum mechanics had yet to uncover. But Einstein wasn't content to simply dismiss quantum mechanics. His 1935 paper with Podolsky and Rosen wasn't just a critique, it was an attempt to show that quantum mechanics, as it was understood at the time, couldn't fully describe reality. They came up with a thought experiment that illustrated their concern. It was a twist on the concept of entanglement, a phenomenon where two particles become linked in such a way that their states are connected, no matter how far apart they are. If you measure one particle, you instantly know something about the other. This happens faster than the speed of light, which posed a problem for Einstein's view of the universe. In the EPR paper, they presented a scenario where two particles are created together and then separated. According to quantum mechanics, once they are separated, measuring one particle's position or momentum should instantly reveal information about the other, even if the two particles are light years apart. This spooky connection, Einstein argued, suggested that quantum mechanics was incomplete. It couldn't possibly describe physical reality because it required non-local interactions, meaning information about one particle was somehow transmitted instantaneously to another. This went against everything Einstein believed about the universe, where nothing could travel faster than the speed of light, and where every effect had a cause that could be traced back to some preceding event. Einstein's challenge wasn't just theoretical. He believed that, if quantum mechanics was correct, it would have to be tested. And so, the world of physics waited. Could quantum mechanics be proven? Could these so-called hidden variables that Einstein believed existed be found? The debate raged on for decades, with Einstein's belief in a deterministic universe standing in opposition to the probabilistic nature of quantum theory. As the years went by, experimental physicists began to test the implications of Einstein's challenge. The first real breakthrough came in the 1960s with a physicist named John Bell. Bell proposed what's now called Bell's theorem, which was designed to test whether the strange predictions of quantum mechanics could be true. Bell's theorem showed that if quantum mechanics was correct, certain kinds of correlations between particles, called Bell inequalities, would be observed in experiments. If hidden variables existed, however, these correlations would not be observed. Bell's work set the stage for a series of experiments in the 1970s and 1980s that would put Einstein's ideas to the test. The experiments involved sending pairs of entangled particles in opposite directions and measuring their properties. According to quantum mechanics, the particles should remain connected, and measuring one should instantly influence the other, even if they were far apart. If hidden variables were at work, the correlation between the particles should be weaker than what quantum mechanics predicted. As experiments progressed, the results were clear. The strange, non-local connections predicted by quantum mechanics were real. Particles did indeed influence each other instantly, regardless of the distance between them. Einstein's hidden variables were nowhere to be found. It was a stunning victory for quantum mechanics, and a major blow to Einstein's deterministic view of the universe. However, this doesn't mean Einstein was wrong about everything. While quantum mechanics had triumphed in this specific area, there remained much to be explored. Einstein's belief that the universe was governed by deep, underlying laws was not entirely misplaced. In fact, his work on relativity opened the door for many of the quantum phenomena we study today. But when it came to the strange and seemingly paradoxical world of quantum mechanics, Einstein's view of a predictable, orderly universe couldn't accommodate the mysteries revealed by the quantum world. So where does that leave us today? Well, despite the victories of quantum mechanics, we still don't fully understand the deep implications of these quantum phenomena. We've learned that particles can indeed be in multiple places at once, that observing something can change its outcome, and that particles can influence each other instantly. But the questions Einstein posed about the nature of reality remain still unanswered in many ways. Perhaps the biggest question left is this: is the universe truly as strange as quantum mechanics suggests? Or is there a deeper, more hidden reality behind it all? The debate between Einstein's worldview and quantum mechanics continues to shape the direction of modern physics. And even as we unlock new mysteries, we're left with the same awe and wonder Einstein felt when he first encountered quantum mechanics, the mystery of how the universe really works. The double-slit experiment. It's one of those experiments that, at first glance, seems too strange to be real. A classic in the annals of modern physics, it's both celebrated and feared. But what it reveals about the universe is nothing short of mind-bending. Imagine this. You take a single electron, a tiny fundamental particle of matter, and send it through a barrier with two slits. You would expect that, like a small ball rolling through a hole, the electron would go through one slit, right? After all, it's just one electron. Simple. But what if I told you that the electron doesn't behave like that? What if I told you it does something far stranger? Instead of going through one slit, the electron behaves like a wave, spreading out and passing through both slits at once. And that's not just an idea or a hypothetical. It's exactly what happens. The electron, when not being observed, acts as if it's everywhere at once, spreading its influence through both openings in space. Now let's step this up a notch. What happens if we decide to watch it? If we place a detector at one of the slits, monitoring the electron as it approaches? When we observe it, really focus our attention on it, something unexpected happens. The electron stops being a wave and suddenly becomes a particle again, choosing one slit over the other, as if it were following some classical rule of behavior. It sounds like something out of science fiction, doesn't it? You could almost hear the words, "Reality is just a simulation," echoing in your mind. But this isn't fiction. This is science, and it's perhaps the most puzzling aspect of quantum mechanics. Because here's the kicker. The electron doesn't just act differently when we look at it. It's as if the act of observing, of placing attention on the electron, actually creates its behavior. It's as if reality doesn't fully exist until we decide to observe it. This is where things start to get really unsettling, because what it suggests is profound. It suggests that observation doesn't simply affect reality in the way we might influence a leaf falling from a tree by, say, blowing on it. No, this is far deeper. This suggests that observation creates reality itself. And that's not just a curious quirk of quantum physics. It's a challenge to everything we thought we knew about the nature of existence. At first you might think that this is a fluke. Maybe the electron is behaving in an unusual way because it's too small for our classical expectations to apply. But the deeper you dive into the double-slit experiment, the more troubling it becomes. Let's revisit the setup. The experiment is simple in design. A particle, be it an electron, photon, or even an atom, is shot through a barrier with two slits. On the other side of the barrier is a screen that will capture the impact of whatever comes through. If particles behaved like little balls, you'd expect to see two bands on the screen, corresponding to the two slits. After all, the particle should just choose one slit to go through. But this isn't what happens. Instead, when no one is watching, the electron forms an interference pattern on the screen, just like ripples in a pond when you throw two stones. This means that the electron behaves as if it's both particles and waves at the same time, something that's difficult to picture in our everyday, macroscopic world. Now we introduce an observer. You place a detector at one of the slits, hoping to know which slit the electron passes through. But as soon as you observe the electron, the interference pattern disappears. Instead of a wave-like behavior, the electron acts like a classical particle, choosing one slit over the other. This is where things get really interesting, and honestly, a little frightening. What happens between the electron and the observer? How does the act of observation fundamentally change the electron's behavior? One of the strangest aspects of this experiment is that it doesn't matter how hard you try to observe the electron. Whether you look at it through a sophisticated measurement device or just observe it with your eyes, the outcome is the same. The wave function collapses. The electron will choose a path, behaving like a particle, and the wave-like interference pattern will vanish. So, what's going on here? Are we saying that the act of observation itself creates reality? Or is there something more subtle happening, something we can't quite grasp? It seems that in the quantum world, the very presence of an observer alters the outcome of the experiment. In some sense, the electron's decision to behave as a particle or a wave depends entirely on whether or not it is being watched. This leads to an even more fundamental question. Does the world exist in the way we think it does, independent of our awareness of it? Now, of course, the implications of this are immense. If we truly live in a universe where the act of observation shapes reality, then what does that mean for everything else we know? Does consciousness play a role in creating the world around us? And more to the point, could the universe itself be constantly shifting and changing, waiting for an observer to notice it, to bring it into existence? There are numerous interpretations of quantum mechanics that try to answer these kinds of questions. Some scientists suggest that the wave function collapses when a conscious observer is involved, while others propose that the universe doesn't have a definite state until it is observed. Some physicists even theorize that everything exists in a state of potentiality, and only when we observe it does it materialize into something we can experience. Perhaps the most mind-bending interpretation comes from the realm of simulation theory, which suggests that our entire reality could be a simulation, much like a video game or a virtual reality experience. If this were true, then the act of observing the electron could be likened to clicking a button in a video game, activating a particular part of the simulation as you interact with it. But let's take a step back and think about what all this means in a broader sense. If observation truly creates reality, then what happens when we observe ourselves? Are we, as conscious beings, somehow shaping our own existence by merely being aware of it? Could the act of thinking about the universe change the very fabric of space-time itself? These are questions that challenge the very nature of our existence, and while no one has the definitive answer, the implications of the double-slit experiment continue to resonate through every field of science and philosophy. As we ponder this strange outcome, we're left with a lingering sense of mystery. Could it be that the universe doesn't just exist as a fixed set of laws and objects? Could it be that reality, in some deep, fundamental sense, needs us to observe it in order to fully take shape? The double-slit experiment, with its paradoxical and confounding results, reveals a universe that's far stranger and more flexible than we ever imagined. It challenges the boundary between science and philosophy, inviting us to reconsider what it means to live in a world of endless possibilities and infinite potentials. In the end, the only certainty we have is that the universe is not as solid and predictable as we once thought. It's a dance between particles and waves, between the known and the unknown, and it might just be waiting for us to pay attention so it can show us what's next. The end of separation. Two particles, born from the same event, shot in opposite directions, each on its own cosmic journey. But here's where things get strange. No matter how far apart they travel, across galaxies, past stars, through the fabric of space, if you measure one, the other responds immediately. It's not just really fast, it's instant. This mind-bending phenomenon, known as quantum entanglement, doesn't fit with anything we've known about how the universe works. Einstein famously called it spooky action at a distance, and it's easy to see why. It goes against everything we thought was possible, especially his theory of relativity, which firmly stated that nothing could travel faster than light. But the strange part, the experiments back it up. Real, repeated, peer-reviewed experiments. Over the past century, scientists have tested entanglement again and again, and each time the results are the same. The particles stay connected, even across vast distances. As soon as one particle is measured, the other responds as though it knew what was happening the moment before, and it happens instantly, with no delay, regardless of how far apart they are. The story of how we came to understand this begins with John Bell, a physicist in the 1960s who sought to test the very foundations of quantum mechanics. Bell's theorem gave us a way to test whether entanglement could be explained by a hidden variable, some unknown factor we hadn't yet understood. In other words, could there be a local explanation, one where the particles weren't actually connected in a spooky, instantaneous way, but instead were just guided by unknown variables, moving faster than we could track? Bell's theorem laid the mathematical groundwork to make this test possible, and the results were nothing short of revolutionary. Over the decades, countless experiments have confirmed that the phenomenon isn't just a fluke or an artifact of the experiment. Entanglement is real. But what does that mean for our understanding of the universe? For decades, scientists assumed the universe was built on a principle of local realism, meaning that everything is only influenced by what's close to it. If you want to know about one object, you need to interact with it, and everything obeys the speed limit of light, no matter what. Entanglement shattered that assumption. The particles weren't confined by space or time. No matter how far apart they were, once one was measured, the other reacted immediately. The very fabric of reality had a hidden layer of interconnectedness, and it wasn't just happening at the scale of particles. It implied something far deeper, something cosmic. The implications are vast. If particles are connected across space instantly, then perhaps space itself is an illusion. Or maybe our understanding of time is incomplete. Could it be that what we experience as separate objects in the universe are in fact deeply intertwined, just as quantum mechanics suggests? Could space, as we know it, not actually be a rigid container, but something more fluid, something that doesn't actually separate us from anything, but connects everything? In the world of quantum mechanics, distance isn't a barrier, it's a perception. When two entangled particles can affect each other no matter how far apart they are, it seems to point to a universe far stranger than we ever imagined. The universe is non-local, which means that distance doesn't define the limits of influence or connection. And yet, this is the reality we live in. This paradoxical, mind-bending universe where particles are entangled and interconnected in ways that defy the logic we grew up with. The world as we see it, with its clear distinctions between objects and space, may not be the whole story. There's a deeper, more intricate web of connections that we're only beginning to glimpse. To make sense of all this, consider a simple analogy. Imagine you're playing a video game, and your character is moving through a vast, open world. You can walk in any direction, explore different realms, and interact with objects scattered throughout. But what if, in this game, there was a hidden layer where all the objects, no matter how far apart they seemed, were actually connected? When you touched one object, it would send a signal to another, even if that object was miles away within the game's world. No matter the distance, no matter the apparent separation, everything in the game would be interconnected, each part influencing the other instantaneously. This is a rough analogy for quantum entanglement, where the particles, though separated by vast distances, still influence each other as though they were in the same place. The boundaries we think exist in our world might not be so solid after all. But there's a challenge here too. As awe-inspiring as entanglement is, it's easy to fall into the trap of overstatement. When we hear that distance isn't real, it can sound like a bold declaration. And sure, the experiments support the idea that entanglement breaks the conventional rules of space, but we still don't fully understand how this all works. The language of quantum mechanics is full of paradoxes and puzzles that leave us with more questions than answers. That's the essence of quantum mechanics, its ability to shake our foundational beliefs about the nature of reality. The more we learn, the more we realize just how much we still don't know. But that's also the beauty of it. It's a constantly unfolding mystery, revealing more and more layers of connection, complexity, and wonder. So, as we venture further into this cosmic journey, one thing becomes clear. Separation, as we understand it, may not be real, or at least not in the way we thought. The entangled particles are a glimpse into a universe where distance is merely a perception, a veil that hides the deep interconnectedness of all things. And the more we study these phenomena, the more we realize that the universe, in its deepest form, is not separated by time or space. It's one vast, interconnected whole. The entangled particles are a cosmic reminder that the universe doesn't follow our simple rules of separation and isolation. Instead, It operates in ways that transcend the very fabric of space and time. As we continue to explore this strange, entangled reality, we're left with one crucial question. If the universe is non-local, what else might be true? What other boundaries, what other assumptions might we be holding on to that no longer apply in a world where everything is connected beyond space and time? The answers are still out there, waiting for us to discover them. Time might not be real either. If space is an illusion, what about time? Imagine for a moment that time doesn't exist the way you think it does. What if it's not a continuous river we're flowing down, not this unstoppable force guiding us from one moment to the next, carrying us inevitably into the future? Instead, what if time is simply an illusion, a trick of the mind, designed to make sense of the vast complexity around us? This might sound like the stuff of science fiction, but it's actually a question that has intrigued physicists for decades. In fact, some researchers believe that time, as we experience it, isn't fundamental at all. What if time is simply an emergent phenomenon, something that arises from deeper, more fundamental principles we don't yet fully understand? To start, let's take a step back and look at how we usually think about time. You wake up in the morning, you check your watch, you see it's 7 a.m., and you get moving. You know the clock is ticking, and it's counting down to something, the future. That's the reality most of us live in, a world where time marches forward, second by second, minute by minute, hour by hour. But what if this idea of time, this steady march of moments, isn't quite as real as we think? In 2019, a team of researchers at Dartmouth College and other institutions proposed an intriguing idea. What if time isn't fundamental, but is instead something that emerges from the deeper structure of the universe? They modeled a universe where time was an illusion, a byproduct of something else happening at a more fundamental level. According to this view, time would be a tool, our brain's way of organizing the constant flow of information, rather than something that exists outside of our perception. To put it simply, imagine time not as a river, but as a construction of your own mind, an internal mechanism your brain uses to make sense of the changes happening all around you. What if the passing of time, this sense of past, present, and future, is simply how our consciousness organizes and tracks events? This isn't just a philosophical thought experiment. It has deep implications in quantum mechanics too. In fact, in the strange world of quantum physics, time doesn't always show up in the equations that describe reality. Quantum mechanics, which governs the behavior of the smallest particles in the universe, often works just fine without time being explicitly included. This has left physicists scratching their heads. If time is so fundamental to how we experience the world, why doesn't it seem to be essential when describing the building blocks of the universe? It's almost as though time, in the quantum world, doesn't even matter in the same way it does in our everyday lives. The behavior of subatomic particles doesn't rely on the passing of time in the way we think it should. Some equations seem to work perfectly well whether or not time is included. And in the heart of quantum mechanics, where particles can be in multiple states at once, where the rules of classical physics break down, time becomes even more elusive. Now let's look at something even stranger. What if what we perceive as the past isn't a fixed, unchangeable thing at all? What if the past is just a collapsed quantum state, an arrangement of information that's already been settled, in a sense, by the act of observing it? The past, in this view, wouldn't be a series of events that happened in a linear, irreversible sequence. Instead, it could be seen as a snapshot of possibilities that have collapsed into a specific outcome, a single point of information that now exists in our minds as history. This leads to another fascinating question. What about the future? If the past is just a collapsed quantum state, then what about the future? Could it be nothing more than a cloud of probabilities, a hazy, ever-shifting set of potential outcomes that might never become concrete? In quantum mechanics, particles exist in a state of probability until they are measured and their behavior becomes defined. Perhaps the future works the same way, an undefined, fluctuating sea of possibilities, shaped by the interactions of particles and forces in ways we can't predict. If this is the case, then time might not be this rigid, unyielding force we imagine it to be. It could be something that we, as conscious beings, create in order to make sense of the flow of information around us. We may think of time as a sequence, a line stretching from the past, through the present, and into the future. But what if that line isn't real? What if it's just a mental construct, a framework our brains use to make sense of the world? Think of it like this. Time could be something like a loading bar in a video game. When you're playing, you see that bar filling up, marking the progress of the game as it loads new levels, new environments, new challenges. In that moment, the bar gives you a sense of time, an idea of how much longer you'll need to wait. But in reality, that bar is just a symbol, a representation. The game is happening regardless of the loading bar, and the experience of time is just your brain's way of tracking the process. You're not actually moving through time the way the bar might suggest. You're just experiencing a flow of information, and your consciousness creates the illusion of progression. In this analogy, time isn't a universal force, pushing us along in a single direction. It's more like a tool our minds use to stay grounded in the vast sea of changing information. Our perception of time may help us make sense of cause and effect, but that doesn't necessarily mean time exists in a real, fundamental way. What's even more fascinating is how these ideas can change the way we think about the very nature of reality. If time is an illusion, if it's something our consciousness creates rather than something we travel through, then everything we take for granted about the past, present, and future could be up for grabs. The universe as we experience it might not be the universe as it truly is. This opens up a vast landscape of possibilities. Perhaps everything we see, hear, and feel is just part of a mental construct, a story our minds tell ourselves to make sense of the world. The past isn't an unchangeable record of what happened, and the future isn't a set of fixed events waiting to unfold. Instead, they are both simply constructs, ways our minds create order out of the chaos of existence. Of course, this isn't to say that time, or the experience of it, is entirely meaningless. Time still plays a crucial role in how we navigate our lives. It shapes our understanding of cause and effect. It governs our physical experiences, and it keeps our universe from descending into total chaos. But the idea that time might be an illusion challenges our understanding of what's really going on beneath the surface. Perhaps time is simply a reflection of the way we interact with the world. Maybe the universe itself doesn't adhere to the rules we've set out for it. Perhaps the universe is far stranger than we can comprehend, and our minds, in their quest for understanding, create the illusion of time to help us make sense of the ever-changing reality around us. If time doesn't exist in the way we think it does, it begs an even bigger question. What does that mean for the nature of reality itself? If time isn't the steady, unchanging river we believe it to be, then what else are we misunderstanding about the world? What else is an illusion, a trick of the mind designed to make the infinite complexity of the universe easier to handle? And maybe, just maybe, the answer to these questions lies in a deeper understanding of consciousness. If time is an illusion we create, could our experience of reality itself be a similar construct, one our minds build to keep us tethered to a universe that is otherwise beyond our grasp? Could the universe, in some sense, be an extension of our own consciousness, with time and space simply tools we use to navigate it? In the end, whether or not time is real isn't just a question for physicists. It's a question that touches the very heart of what it means to be human. As we peer deeper into the mysteries of the universe, we are faced with a profound truth. The more we understand, the less certain we become about the nature of reality itself. Perhaps the only thing that's certain is this: time, as we know it, might not be real after all. But in the grand scheme of things, does it really matter? The holographic principle, The universe you see, feel, and experience isn't exactly what it seems. You look up at the stars, you touch objects around you, you breathe in the air, and everything feels real, doesn't it? But what if this entire reality, the space you occupy, the time you experience, even your own consciousness, were all just a projection, a grand illusion, painted on a distant boundary, far from your grasp? This is the essence of the holographic principle, a groundbreaking idea that emerged from the depths of theoretical physics, challenging our very understanding of reality. To unravel this idea, we need to travel back to the 1970s, a time when two brilliant minds, Jacob Bekenstein and Stephen Hawking, stumbled upon something strange and profound while exploring the nature of black holes. What they discovered would forever change the way we look at the cosmos. At the time, black holes were mysterious objects, pulling in everything around them with such force that even light couldn't escape. But Bekenstein and Hawking found something curious. The amount of information contained in a black hole wasn't tied to its volume, the space inside it, but rather its surface area. This observation was a turning point, leading them to propose a concept that would echo through the corridors of modern physics, the holographic principle. The idea is deceptively simple but profoundly challenging to grasp. It suggests that, much like a hologram, the information that makes up our three-dimensional universe is not stored within its volume, its depth, but rather on its two-dimensional surface. What if, instead of the universe being a vast, infinite expanse, everything we know and experience is actually a projection from a boundary, a distant surface, a boundary that might not even be located in the place we call space? This idea draws a striking parallel to the nature of black holes. Just as the information inside a black hole seems to be encoded on its event horizon, the boundary marking the point beyond which nothing can escape, perhaps the entire universe is a sort of cosmic projection, with its fundamental information lying on a two-dimensional surface, far removed from where we live. To understand this, picture a two-dimensional surface like the surface of a sphere. While the sphere itself is three-dimensional, everything you experience as a being living on the surface, every up, down, and around, is a projection of the information encoded on that surface. In the same way, our reality could be a projection from a boundary, existing far beyond what we can observe. What's even more mind-boggling is that the math behind the holographic principle works. It fits the equations, aligning with both general relativity and quantum mechanics. The most mind-blowing part? This isn't just a theoretical curiosity. It's one of the most widely accepted models in theoretical physics today. The concept is not entirely new. It stretches back to ideas that physicists have been toying with for years. The famous string theory, which seeks to explain the universe at its most fundamental level, lends support to the holographic principle. String theory suggests that the fundamental building blocks of the universe aren't particles like atoms or electrons, but rather tiny, vibrating strings of energy. These strings can exist in more than 3 dimensions, and their behavior may provide the key to understanding the holographic nature of reality. In this framework, the universe we perceive may be a mere reflection of the interactions of higher dimensional objects projected down into the dimensions we experience. Think of a hologram, a 3D image encoded onto a flat surface. You can look at it from different angles, and it appears three-dimensional, even though it's just a 2D projection. The holographic principle proposes that the universe works similarly. What we experience as depth, space, and time might be an illusion, a projection of information encoded in a lower dimensional space. While this might sound like something out of a science fiction novel, the implications are profound. It suggests that our entire reality, everything from the galaxies to the smallest particles, even time itself, could be the result of information encoded in a lower dimensional surface. Imagine our universe as a cosmic movie, where the 3D images we see are the result of a more complex hidden reality that lies just beyond our comprehension. This perspective challenges not just our understanding of space and time, but also the nature of existence itself. If the holographic principle holds true, what does that say about the nature of consciousness? Could our awareness, our very sense of being, be a projection from this hidden boundary as well? What happens when we start to consider the possibility that everything we experience, our thoughts, our emotions, our sense of self, is part of this cosmic hologram? At the heart of the holographic principle is the search for a unified theory of physics, one that could bring together the realms of quantum mechanics and general relativity, two pillars of modern physics that, to this day, remain stubbornly incompatible. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the behavior of massive objects like stars, planets, and black holes. The holographic principle offers a potential bridge between these two worlds, suggesting that the information about particles and the fabric of space itself might be stored in a way that transcends both realms. This idea has already made waves in our understanding of black holes, a place where the laws of physics seem to break down. As we peer into the heart of a black hole, we encounter a region where gravity becomes so intense that space and time themselves are warped beyond recognition. The holographic principle may offer a way to reconcile the seemingly contradictory nature of black holes, suggesting that the information we think is lost inside them might instead be encoded on their event horizons, the very surface that marks their boundary. This insight leads to the heart of a cosmic mystery. What happens when we look at the universe through the lens of the holographic principle? We might find that the universe is not a vast, infinite expanse, but rather a delicate projection, like the intricate pattern of a hologram. In this view, space, time, and everything within them could be the result of complex interactions between information at the boundary of the universe. It would be as if we are looking at the universe from the inside of a cosmic mirror, experiencing a reality that is far stranger and more mysterious than we could have imagined. While the holographic principle is still a theory, and not everyone in the scientific community accepts it, its potential to explain the nature of reality is undeniable. It invites us to reconsider everything we thought we knew about the universe, and it challenges us to embrace the possibility that we are not seeing the full picture. Our experience of reality, as rich and tangible as it seems, may be nothing more than a reflection of something far deeper, a projection from a boundary beyond our comprehension. In the end, the holographic principle invites us to look at the universe in a whole new light. It asks us to consider the possibility that everything we experience, every star, every galaxy, every atom, is just a tiny piece of a much grander cosmic picture, one that is still waiting to be understood. And as we peer into the depths of this mystery, we can't help but wonder, are we simply projections of a greater truth? Or is the truth itself simply a projection? Reality as information. When John Archibald Wheeler, one of the most influential physicists of the 20th century, said, "Everything physical is information, theoretic in origin," he wasn't just making a philosophical musing. He was proposing a radical rethinking of the nature of reality itself. To Wheeler, the universe isn't a collection of solid, immutable objects. Instead, everything you experience, every particle, every force, every galaxy, is, at its core, information. Let's pause for a moment. You might be thinking, what does that even mean? How can reality be made of information? It's a question that challenges the way we've always understood the world. But in this strange, fascinating universe of ours, it might just be the key to understanding some of its deepest mysteries. Imagine this for a second. You're not really made of atoms. Or, to be more precise, you're not made of just atoms. Instead, you are the result of information, the data that describes those atoms. Every thought you have, every feeling you experience, every action you take is just a process of interpreting data. Your brain isn't directly experiencing the world as it is. What it's actually doing is processing signals. electrical signals to be specific, that represent the sensory information coming from the world around you. But where does this data come from, and what does it even mean? It all starts with the idea that everything in the universe can be boiled down to information. This is where Wheeler's famous phrase, "it from bit," comes into play. The bit here is shorthand for a basic unit of information, a binary choice, like 0 or 1. In the same way that a digital computer stores information in bits, Wheeler was suggesting that the universe itself functions as a kind of cosmic computer, processing data to produce the reality we observe. In this view, reality isn't a tangible, physical object. It's a dynamic process of information being created, processed, and transmitted across time and space. Think about it like this. You're sitting in front of a screen, watching a video. The pixels on that screen are just tiny bits of information, but together they form an image. The image is only meaningful because your brain knows how to interpret it. Without your brain's ability to process the data, the pixels are just meaningless points of light. In the same way, the universe's pixels, the fundamental particles and forces, only take on meaning when they are processed by something capable of interpreting them. Whether that's a human mind, a machine, or even the universe itself, the act of interpretation is what gives these bits of information their purpose. This leads to some mind-bending ideas about the nature of reality. If everything is information, then what we perceive as solid objects, like trees or mountains or even stars, are just interpretations of data that exists at a much deeper level. What we see, touch, and interact with isn't the thing itself, but the way our brains process the information about that thing. So in a way, you could say that everything you experience is a simulation, but not in the sense of a video game or computer-generated world. It's more like the universe itself is processing information, and we're just one of its many interpretations. Now you might be thinking, okay, that's a wild idea, but does it actually work? Can we find evidence of this information-based view of reality? The answer is yes, though it's not always easy to wrap our heads around. Take the phenomenon of quantum entanglement, for example. It's one of the most puzzling aspects of quantum mechanics, and it's a perfect example of how information can shape reality in ways that defy classical intuition. In entanglement, two particles become linked in such a way that the state of one particle immediately influences the state of the other, no matter how far apart they are. In other words, if you measure one particle, the other particle's properties are determined instantly, even if it's light years away. But how can information travel faster than light? Isn't that a violation of the laws of physics? The key to understanding entanglement lies in recognizing that the distance between particles isn't as straightforward as we might think. In the information-based model of reality, there's no need for information to travel through space. Instead, the two particles are part of a larger, interconnected network of information. When you measure one, you're simply accessing the information stored in the network, no travel involved. This view also helps us understand some of the most bizarre aspects of the famous double-slit experiment. In this experiment, particles like electrons or photons are fired at a screen with two slits in it. If the particles are observed, they behave like tiny particles, passing through one slit or the other. But if they're not observed, they behave like waves, creating an interference pattern on the screen. The key here is the act of observation. When you measure the particles, the information about their position is revealed. Without measurement, the particles exist as a wave of possibilities, until the information is collapsed by the observer. So what's going on here? In the traditional view of physics, we'd say that particles have definite properties, whether or not they're observed. But in the information-based view, the act of observation doesn't just reveal a pre-existing state of affairs, it creates that state. Reality in this sense is not a fixed thing. It's a process that unfolds as information is gathered and interpreted. This idea of reality as information also helps explain the strange, almost intangible nature of time. Time seems to flow in one direction, from past to present to future. But what if this flow of time isn't a fundamental feature of the universe, but rather a consequence of how information is processed? In the information model, time isn't something that exists independently of us. It's a byproduct of the way we organize and interpret data. In other words, time feels like it flows because we're constantly processing new information. We don't experience a static, unchanging reality. Instead, we experience a constantly evolving stream of data, which we perceive as time. If you think about it, this is similar to how we experience a movie. A movie doesn't move. It's a series of still images played one after another. But because the images change so quickly, we perceive motion. Similarly, the constant flow of new information gives us the experience of time. The beauty of this view is that it doesn't require us to discard the rules of physics we know and love. The information-based model is still grounded in the science of the universe, but it asks us to think about those rules in a different way. Instead of seeing the universe as a collection of physical objects interacting according to fixed laws, it invites us to see it as a vast network of information being processed and interpreted in ways that we're only beginning to understand. As wild as it sounds, Wheeler's insight into the nature of reality may be one of the most profound ideas to emerge from modern physics. It suggests that the universe is not just a machine operating in the background, but a living, dynamic process, a process that we, as conscious beings, are part of. Reality, in this sense, is not something separate from us. It's something we're co-creating as we interact with it, interpreting the flow of information that makes up the cosmos. But this raises even bigger questions. If the universe is made of information, what does that mean for our understanding of consciousness? Are we, too, just part of this cosmic information process? Is the universe itself conscious, interpreting its own data, just as we interpret ours? And if reality is truly a product of information, what happens when the data changes? These are the questions that Wheeler's radical vision opens up, a vision that challenges everything we thought we knew about the world and invites us to explore the deepest mysteries of existence itself. The simulation theory. As we venture deeper into the unknown, the lines between reality and illusion begin to blur. Everything we call real, the stars, the earth beneath our feet, even our thoughts, has been questioned, dissected, and examined. And with every new discovery, an unsettling thought emerges. What if this isn't real at all? What if the very world we inhabit is nothing more than a sophisticated simulation? The more we learn about the nature of reality, the more plausible this idea seems. It's a concept that has intrigued philosophers, scientists, and dreamers for centuries, but only in recent decades has it begun to find a foothold in the scientific community. Could we really be living inside a simulated universe? At first glance, the idea sounds like pure science fiction. After all, how could something as vast and complex as the universe be reduced to mere code? But the more we dive into the mysteries of quantum mechanics, the more we realize that reality is not what it seems. Take, for example, the strange behavior of particles in the quantum realm. At the subatomic level, particles don't follow the predictable laws of classical physics. They exist in a state of probability, in multiple locations at once, and only choose a position when they're observed. This phenomenon, known as wave-particle duality, suggests that the very fabric of reality is shaped by observation itself, as though the universe is responding to our awareness. But it doesn't stop there. In 1999, physicist James Gates made an astonishing discovery while studying the equations of string theory. He found that the equations themselves contained something that looked suspiciously like error-correcting code, information typically used in computer programs to correct mistakes. This revelation wasn't just a small curiosity, it was a profound hint that the universe, at its most fundamental level, might be operating on principles that are eerily similar to the digital world of computers. Gates's discovery opens up a whole new line of inquiry. Could the universe, with all its complexities and apparent randomness, be built on a set of algorithms, like the code that runs a video game or a virtual world? Could we be living in a vast simulated landscape, unaware of the underlying system that powers it? It's a question that's gained traction in recent years, particularly with the work of philosopher Nick Bostrom. In 2003, Bostrom proposed what's known as the simulation hypothesis, a bold, thought-provoking theory that has since captured the imagination of many. Bostrom suggested that if any civilization advances far enough technologically, it could create simulations of entire universes, complete with conscious beings. And if such civilizations run many simulations, the probability that we're living in the one real universe becomes almost infinitesimally small. In other words, if simulations are possible, and they're created by many civilizations over time, then the odds are overwhelmingly in favor of the idea that we, too, are living in one of them. This doesn't mean that we're just characters in a video game, with programmers controlling our every move. Instead, it suggests that we might be living on a platform so advanced, so deeply embedded within the very fabric of our reality, that we can't even begin to comprehend it. Like a character in a game who is unable to see the console, we might be trapped within a structure so intricate and vast that we can't even recognize the underlying mechanisms. But how do we know if we're in a simulation? The truth is, we don't. At least not yet. Our understanding of the universe is still in its infancy. We've only scratched the surface of quantum mechanics and string theory, and the tools to detect a simulation, if it exists, may be beyond our reach. However, some scientists believe that there may be subtle glitches in the fabric of reality, irregularities in the laws of physics, or inconsistencies in how information behaves that could reveal the underlying structure of the universe. Consider the fact that, at the quantum level, particles appear to behave in ways that defy logic. There are instances where particles seem to exist in two places at once, or travel backward in time, or even influence each other across vast distances without any apparent connection. These bizarre phenomena, known as quantum entanglement, have left scientists scratching their heads for decades. Could these oddities be signs that the universe is not as solid as we think, that it's really just a set of coded instructions running in the background? One of the most compelling aspects of the simulation hypothesis is its connection to the nature of consciousness. If we are indeed living in a simulation, then what does that say about the nature of our minds? Are we simply following a pre-programmed set of instructions, or do we have true agency and free will? This question touches on some of the deepest mysteries of existence: what it means to be conscious, what it means to be real. Interestingly, some aspects of ancient philosophy seem to echo the idea that reality is not what it seems. In the philosophy of Vedanta, for example, the material world is seen as an illusion, Maya, and true reality is understood to be an underlying, non-material consciousness. The idea that the world we perceive is merely a projection or manifestation of a deeper truth is remarkably similar to the concept of a simulated universe. Perhaps in some sense, the ancient sages were already pointing to the possibility that reality is not what it appears to be. In the end, the simulation hypothesis raises more questions than answers. If we are living in a simulation, who or what created it? What is the purpose of our existence? And perhaps most importantly, what does it mean to be real in a world where everything may be constructed from information? For now, these questions remain unanswered, but the possibility that we might be living in a simulation is no longer the realm of science fiction. It's a legitimate theory that is being explored by physicists, philosophers, and computer scientists alike. And whether or not we're able to prove it in our lifetime, the very notion forces us to rethink the nature of reality and our place in the cosmos. As you stand here, staring at the vastness of the universe, it's easy to assume that everything around you, the stars, the planets, the very ground beneath your feet, is solid, fixed, and real. But what if everything you think you know about reality is wrong? What if the universe doesn't work like a machine, ticking away in predictable patterns? What if instead, It operates on something far more mysterious and elusive: information. Think about it. Space, as we know it, might not even exist in the way we experience it. It's not the endless vacuum we once imagined. It's a series of interconnected fields, full of dynamic energy, constantly responding to measurement and interaction. Time? It might be a trick, a dimension that bends and stretches, a construct we created to understand the flow of events. And matter? Well, matter isn't really matter at all. It's more like a dense web of probabilities, a cloud of potential that collapses into what we see only when we observe it. This revelation doesn't just challenge our understanding of the cosmos, it asks us to reconsider our very place in it. The universe isn't some distant, objective reality operating outside of us. It's deeply intertwined with our consciousness. When we observe, when we interact with the world, we're not merely spectators. We're shaping reality itself. The act of measurement doesn't just tell us what's happening, it creates what happens. Imagine that every time you look at something, whether it's a distant galaxy or a single grain of sand, you're not simply observing, you're contributing to the unfolding of its existence. You're not separate from the simulation, you're part of it. You're not a passive observer, you're a co-creator of the universe's story. In this vast cosmic theater, maybe the most profound realization is this: you're not outside the code. You're the one reading it, interpreting it, and even rewriting it with each glance. And with every new discovery, the universe shifts and molds itself in response to you. What if the universe isn't just a thing that exists? What if it's a living, breathing interaction, constantly evolving with every observation you make? The universe. As you know, it doesn't exist. So no, physicists didn't prove that the universe isn't real in the sensationalized way some might suggest. There's no evidence that everything we experience is some elaborate illusion or simulation, at least not in the way the headlines often portray it. But here's what they did prove. The universe doesn't behave like a mechanical, isolated machine that exists independently of us. It doesn't operate according to the old rules of physics that were once thought to be absolute and unchanging. Instead, it behaves more like something stitched together from information, an intricate, dynamic web of relationships that are deeply interwoven with our observations and actions. It's a complex, reactive system, constantly shifting and adapting, much like a living organism responding to its environment. This is where things get fascinating. For centuries, we've seen the universe as a collection of solid, immutable things: planets, stars, atoms, and particles. But that's not what the data is telling us anymore. The very fabric of reality is made up of fields, probabilities, and interdependent forces. Things are not separate. They're all part of a larger whole, constantly changing, constantly reacting, and constantly evolving. The concept of observation changing the very nature of what we observe, that's a game changer. It's not just a quirky detail of quantum mechanics, it's a fundamental truth about how the universe works. The universe, as we thought it functioned, no longer exists in the form we once understood it. What we once saw as fixed and certain is now a fluid, unpredictable dance of energy and information. But here's the big question. If the universe isn't this cold, mechanical thing outside of us, if it's made of information and reaction, what does that mean for us? Are we merely passive observers of this cosmic symphony, or are we part of it? Maybe, just maybe, we're not separate from the universe. We're intimately connected to it, shaping and molding it with every thought, every interaction, and every observation. It's a deeply humbling thought. The universe, as we once imagined it, is gone. And what remains is something far more fascinating, far more intricate, and far more alive than we ever could have anticipated. The lines between subject and object, between you and the cosmos, are starting to blur. What was once an external reality is now a co-creation. You're not just watching the universe unfold, you're participating in it. And so, we are left with a universe that is less about fixed matter and more about interaction, less about the physical and more about the informational. But that doesn't mean we understand it all. In fact, the more we learn, the deeper the mysteries seem to grow. Maybe we'll never know what's really under the code, or whether there even is an outside to all of this. But what we do know is this: the universe isn't what it used to be. It's something much stranger, something much more wondrous, and we, it seems, are a part of it in ways we never could have imagined. So what does this mean for the future of science, for our understanding of reality? We'll have to keep exploring and questioning, because the answers are far from over. And as we continue to probe the depths of the universe's mysteries, one thing is clear: we've only just begun to scratch the surface. If you found this journey mind-boggling, drop a comment below and share what fascinates you the most about the topic. And if you haven't already, don't forget to like the video and subscribe to the channel so you don't miss out on our next deep dive into the mysteries of the universe. Thanks for watching, and keep questioning everything, because the universe is far stranger than we can imagine.